new lecture from Computer Vision Bootcamp. Today, we'll be spending some more time on UNet and some of the variants of UNet. And basically, the task that we'll be still working on in today's lecture will be image segmentation. But in addition to what we did in the last lecture, which was predominantly dedicated to understanding the architecture of UNet in detail, this time we'll be coding a UNet for two different data sets. And one additional thing that I decided we could do is host a pre-trained UNet model weights on Hugging Face so that anybody could inference from the model. Basically, anybody could use the model for their segmentation task for this specific type of task. So I'll be also be introducing you to Hugging Face a little bit in case you are not aware of the platform itself. So we'll start as if we are complete beginners. So starting with the variants that we are briefly going to look at today, UNet we already discussed in detail in the last lecture. I will be providing a very brief recap on what we learned. But today we'll be discussing briefly about three architectures, UNet++, Attention UNet, and Residual UNet. But looking at the citations that these papers have, the UNet paper has almost 2 orders of magnitude higher number of citations. This has 118K plus, but the other papers have in the range of 1K, 10K-ish. So from a popularity point of view and from a, I would say, scientific breakthrough point of view, nothing beats UNet yet. But we'll be looking at what people did in addition to the vanilla UNet architecture, which was introduced in 2015, and how did it change the overall utility of UNet. So just to have a brief recap in UNet, as we discussed last time, UNet has mainly 4 parts to pay attention to. First is encoder. Encoder is everything to the left of this line. So it's like a very symmetric architecture. This is encoder. And this everything on this right side is decoder. Then what happens in UNet is in the encoder part, the input image, which is originally a grayscale image, it will go through certain transformations. Many of them are convolution operations. So all these are convolution operations. Because there is no padding, the convolution operation reduces the size of the image spatially by a factor of 2 pixels at a time. And then these are max pooling operations, which will directly halve the dimension spatially. And by the time you reach the bottom, and this part is called bottleneck, the last layer, you will have an image of 30 by 30 dimensions. You had started from 572 by 572, but you will have 1024 channels. And then you will go up along the decoder. So encoder tries to make the information as abstract as possible, try to reduce the spatial width and height, but decoder tries to bring it back to the original dimension. But to avoid the valuable information from the encoder section to be lost, you also have these things called as skip connections. So these skip connections directly concatenate the encoded features from the encoder part directly to the same layer in the decoder. So totally there are 4 layers or 4 levels. This is level 1, level 2, level 3, level 4, level 3, level 4, and last one is bottleneck. So this was the encoder-decoder architecture of UNet. We also discussed that a similar type of architecture is utilized in stable diffusion in generative AI, which we won't be going into detail today. Now let's discuss briefly what is the difference between UNet and UNet++. So the only difference in UNet and UNet++ is in the way you propagate the skip connection. In UNet++, you have some intermediate convolution operations shown by these circles. So this architecture, what you see is a simplified version of UNet. This is nothing different. It's just that you are not providing as many details, but this is UNet and this is UNet++. And here the only difference is the intermediate convolution layers, which perform additional operations during the skip connection process, so that you are not directly passing the encoded features, but you are passing them through certain convolution operations before it finally reaches the decoder. So this is the difference between one of the differences between UNet and UNet++. And there are several advantages. The main disadvantage is that training will be slower because now you have more number of parameters to take care of. But the advantage is that when you are performing backpropagation, you have much more detailed connections from your final output to the previous layer. So here you can see that in the final output, so this final output is where you add the features from every single layer. So the first level of the encoder, last level, fourth level of the decoder. Level 1 and level 2, level 1 of the encoder and decoder. I mean to say, this is level 1 of encoder. This is also level 1 of decoder. So you can see that in the output, there are features coming from both of these levels, but also from these intermediate connections in the skip connection region, you are having some outputs. But you might be wondering, okay, if there are 5 outputs like this, how do we perform classification? How do we perform segmentation? Because we just want one mask ideally, right? Or 2 masks, one for background and one for object. So how exactly is it done here? So the way it is done is, in the training part of the UNet++, we will be considering the outputs from all these nodes, and a combined loss function will be created where all these outputs are compared with the ground truth mask. But during the inferencing, you might only look at the output from this node, so that whatever mask this node is predicting is being used for the final segmentation process on the input image. So that's the main difference between UNet and UNet++. And so for certain tasks like biomedical image segmentation, apparently UNet++ have a better accuracy, but I'm sure it's also confined for specific data sets. We can't make blanket statements, but you can see that UNet++ is much more well-connected architecture, much more complex. Of course, inference might be slower. Training is definitely slower. So that's the difference between UNet and UNet++. Now, in residual UNet, before I even show you the image, just by the name, we can imagine that there has to be some residual connections. Residual connections like what? Residual connections like those in ResNet. So in ResNet, as we had discussed in the last lecture, the residual connection was like this. You have an input. The input will go through some convolution operations, and there will be an output. And if this, whatever is coming out here as the output, can be called as f of x and input as x, you are having something called residual, where you add this f of x plus x. So the final output from this ResNet block is f of x plus x. So although the output is this, the residual block in the ResNet is not learning f of x plus x. It's only learning f of x. Remaining x is already part of the input. And the advantage of this is that when you put this multiple times as in a series, you can eliminate the problem of vanishing gradient, because you will have direct connections. The inputs are directly propagated to the output. And because of that, even the earlier layers of the neural network has significant influence on the output. So back propagation will not cause vanishing gradient, because even this layer, even if this is the first layer of a 101 layer neural network, this layer also will influence the neural network output significantly, as we had showed in the previous lecture. So if we look at the ResNet 101 architecture, we can take any random ResNet architecture actually. So just take a look at this, or let's take a look at this. So in this architecture, you can see that there are residuals going all the way till the output. So whatever changes are happening at the input is having an almost direct influence at the output. And because of this, the loss is not just influenced by the later layers, loss is also influenced by initial shallow layers. So just based on this knowledge, we can already imagine that some residual connections where some addition will happen in the residual UNet. In normal UNet, we were not adding the input from encoder into the decoder output. We were actually concatenating. So we will have width times height times number of channels, let's say channels in encoder. And if this is the situation at a particular layer in the encoder, decoder may have a different width, W1, height 1 times number of channels in decoder. So let's say this is level 3. And this is also level 3. And this is decoder. This is encoder, right? Then what was done was you were cropping so that this W1 and H1 are matching this W and H. So this is first copied and cropped. so that this becomes W by H by CD. CD is the number of channels in decoder. And then you will concatenate these two such that the final output will be W times H times CD plus C encoder. So something like this. So width and height will remain same as what is there in the encoder, but the number of channels will be sum of the number of channels in encoder plus decoder. So this is what was happening in the UNet architecture. This will also happen in the UNet, residual UNet, but in addition to that, there is a separate operation which is plus, which is not concatenation. You are adding the values. So the structure basically looks like this. So in every block of the encoder and in every block of the decoder, you can see that there is a residual block. So this guy, this purple dotted box is called as a residual block. And if you look at what is happening in the residual block, you can see that inputs are being propagated from one layer to after the next layer. And then whatever output comes out of that is being added with the input from the previous layer. This plus symbol shows that you are not concatenating, you are adding, similar to ResNet. And this has some level of influence on how much the back propagation can be better during gradient descent process. And this particular architecture, you might notice that this does not have 4 levels. It has only 2 levels. And then finally, there is a bottleneck. And then it has 2 levels in the decoder also, because this particular architecture was used for a smaller biomedical data set. But the residual UNet basic idea is almost same as UNet, except you introduce these residual blocks. These residual blocks ensure that at least within the blocks, there is some good amount of not skip connections, residual connections similar to ResNet. But there is no change in the skip connection. This skip connection will remain the same. So whatever we were doing in the UNet++, we are not doing that in residual UNet. Then there is one more architecture of UNet, which is somewhat popular. There are many other variants also. There are variants where both of these are mixed, where you have dense connections in the skip part of the network, plus you have residuals. So you can have that, but this one is called attention UNet. So don't worry by looking at this, I would say a bit intimidating diagram. I'll explain it module by module. Let's focus on the part of the UNet first. So this is the encoder, bottleneck, decoder. Don't worry about this FHWD. It's like filters, height, width, dimension, depth of number of channels, right? So all of these things are the same. The only difference is now you will see these attention blocks or attention gates. So the purpose of these attention gates is that in normal vanilla UNet, you were passing the encoded features from the encoder. You were not really paying attention to whether those features are actually useful for image segmentation or not. You were directly passing it. The idea of this attention gate is that you will sort of modify the feature, whatever is coming from the encoder, whatever is coming from here, you will modify it a little bit based on what the decoder thinks at the moment is useful. So how do you do that? Just look at the inputs that are going into this attention gate. There is one input coming from the decoder. There is one input coming from the encoder of the same level of this, whatever this is. And then something happens to these inputs such that final output is a much more refined versions of this skip connection. So this is the skip connection plus this is decoder input. Something happens to the skip connection so that it becomes more useful to the decoder, right? Now let's see what is happening. So here, this is whatever input is coming from the skip connection. This is whatever input is coming from the decoder block. Then both of these are added. So here you can see a plus sign. They are being added to create just one single representation of input coming from the skip connection and the current inputs that are encoded in the, or embedded in the decoder part. And then they pass through a ReLU activation function. And then they are passed through a 1-by-1 convolution layer. And following by that, they will pass through a sigmoid. So I'm sure this part of however people figured out why this is useful is very empirical. So from a first principles, I am not sure how much we can explain the utility of, oh, why here ReLU, why not maybe GLU or some other activation function? Why did we use ReLU? It's hard to, we can only explain it in retrospect. But at the end of the day, what is happening is, just look at what's happening to this skip connection. Skip connection is also directly propagated here to the output. So this is still the skip connection. And if this attention gate was absent, so what is attention gate? This whole thing is the attention gate. If this was absent, whatever input comes from the skip connection would have directly went here into the, this is the input going into the encoder to be concatenated. This is what would have happened. And see, this part is like a zoomed in visual of this one attention gate, okay? So in the absence of attention gate, the input from the skip connection would have directly went to the, sorry, this is not encoder, my bad, decoder, would have directly gone to the decoder from the encoder. But here, something is being concatenated to the skip connection. And what is that? Basically, the skip connection plus decoder inputs are added. And then it passes through ReLU, it passes through one-by-one convolution, it passes through sigmoid. And finally, what we are left with is something like a attention mask. And this attention mask is such that the values of this mask is between 0 and 1. So you add them, you add the two channels, skip connection channel and decoder channel, pass through a ReLU activation function. Then you have a one-by-one convolution followed by sigmoid activation. This produces a mask which has numbers like alpha between 0 and 1. So for example, a mask can look like this: 0.1, 0.2, 0.9, 0.3. And this name attention might ring some bell when you compare it with the attention head in the transformer. So attention, if you look at this, or let's say, if you look at the values that are there in the attention matrix in the transformer head, it will also look like they are numbers between 0 and 1. Just wanted to show you this. I don't know how many of you have seen this website. It's like a very nice visualization of transformer in GPT. So just I'm pasting it in the chat. Just check this out. I don't want you to spend too much time right now, but just you can have a look at it later. But let me show you these numbers after normalizing. So here the numbers, it's like a matrix of n by n, and the numbers in each row will sum up to 1, and they are all between 0 and 1. So this is like the way in which transformer will notice how query and key are correlated with each other. That attention is, the name sounds similar, but the attention matrix structure is very different here. Here, what we have is a matrix of, let's say, numbers like 0.4, 0.5, etc. And what this mask, alpha mask, what this says is, how much does this region from the encoder, how much does that region, how much is it useful for final segmentation? So if the value is closer to 0, it means whatever pixels correspond to this particular region from the skip connection, they are not very useful. That is what it means. If the values are, let's say, above 0.5, it means those regions have more utility in final segmentation. So basically, this mask produces a set of numbers for important features and unimportant features. So if alpha is close to 0, the features corresponding to those pixels from the skip connection input are kind of suppressed. If alpha is close to 1, those features are retained. So this way, you are not directly passing the values of the skip connection from encoder to decoder. You are making it pass through an attention mask, and this attention mask either suppresses or keeps whatever features are relevant as such. As such meaning almost as such. You are multiplying with a number close to 1. So now these resampled weighted features, why do we call it as weighted features? Because we are multiplying with these numbers between 0 and 1. They are now passed into the final decoder for concatenation. So this is the primary difference between vanilla UNet and attention UNet. Now, I don't want to spend too much time on the variants of UNet. I want to directly now jump into implementation of the UNet architecture itself. And in the last lecture, we were discussing about 4 use cases. First one was industrial, like pipe crack detection or detection of some kind of structural damage happening. We were discussing about biomedical. We were also discussing about aerial image. And I don't know if we discussed any other self-driving car application or something like that, but you can imagine many other industrial applications for segmentation. So today we'll be looking at one industrial application with a small toy data set, because big data sets will take more time for us to train. We will also look at one use case from this aerial images, again with a smaller data set, but we will try to train the model to the best possible given the time constraint, and we'll try to perform validation on the data set. And after we do these things, one of this, probably this, we will try to host on Hugging Face. So all of us will do this together. And don't worry if you don't know how to use Hugging Face. We will all learn that together today. So with that, let's get started. I will share the Google Colab notebook with you, but please first get started with your Colab notebooks. I'm going to share the code here and I'll explain you it block by block. It's very easy, by the way. It's not a, the UNet architecture is anyway kind of easy architecture. Okay, so please first have this Colab notebook. One more thing I will do is I will share the Google Drive link with all of you. Okay, so this is the Google Drive link for the crack detection on concrete. And for the next exercise that we are going to do, I'll also share that link. So please keep it handy, this aerial segmentation. So do one thing, just make a copy of both of these folders in your Google Drive so that you can run the code yourself. So as usual, first thing is, if you have a GPU access, just try to connect with a GPU or TPU, whichever you have. I have connected with the A100 GPU. As you know, I have purchased the GPU credits on Colab. And here the dataset path for me is this content/drive/my/drive/concrete crack. So this path might vary for you depending on what exactly is the name of your folder in which your data is there. But if you don't change anything with respect to the folder name, you should be able to keep this as such. So I will ask you, so can anyone confirm that once you have the copy of the data set in your Google Drive, is this block of code running for you, importing the data set? So basically, I will just mention how exactly the data set looked like. So the concrete data set looks something like this. It has 2 folders, images and masks. Images are bunch of images of concrete surfaces that looks like this. Can you see the my folder in which these concrete surface images are shown? I'm not sure if I just shared my window or if I am sharing my entire screen. Can anyone confirm if you can see this concrete image? Okay, yeah, thanks. So these are the surfaces, and you can see that there are some surface undulations. Sometimes you will see crack, for example, yeah, like this. So here you can see that there is a crack that has formed, and the corresponding mask is something that looks like this. So if cracks are not there, it will be like a black color thing because there is nothing to annotate. But if cracks are there, here you can see that wherever that crack is there, there is some whitish/grayish color annotation. So this is the data set. And the naming is such that the first file is crack01.png. Image is also crack01.png. Basically, the name of the file, I mean, this is JPG, the other one is PNG. So all the images are of JPG format. All the masks are of PNG format, but the file name is the same. So that's the way in which you can go, you know which mask is corresponding to which image. Then the other data set, I will just describe that briefly as well, is the aerial view data set. And that data set has 8 subsets in which images would look something like this. So these are the images which are almost like, it doesn't look like satellite image. Maybe it's a zoomed in satellite image, but almost like that, of different regions, cities. There are some desert areas. There are some areas with greenery, water, etc. And then masks are exactly the masked representations of those same satellite image shots. And different colors have different meaning. And the meaning is shown in this JSON file. So this JSON file has the description of classes. There is water. Then there is, I don't know if you can read this. This font size is a bit small. There is water. There is land. Then there is a road. There is building. So there are, I think, 7 or 8 different classes in this classes.json, actually 8 classes. So this will be the second data set that we'll be working on. So first, let's do one thing. Let's start running this code. You first import the libraries that we need. These are standard libraries for PyTorch for plotting. Then data loader for creating training and validation data. So nothing fancy here. Then next thing is preparing the data set. So in the data set, we have to define the directory because we have 2 directories, one for images and one for masks. And we have to define those 2. And then finally, we convert image into the tensor format. So we discussed this last time, right? If we have tensorial representation of data, it's better than NumPy representation, and NumPy is better than just the Python list. So NumPy better than list, tensorial representation better than NumPy. So this particular function, functions inside the class is just doing that. So just run the code. Let me know if you're able to run the code, or if you have already finished running the code, just let me know. And we are splitting the training and testing, 80% for training, 20% for testing. Batch size is, in every batch of images, there will be 8 images. Like that, there are 640 images in the training, 160 in the validation. And here we are just displaying one random batch, and you should see that the images and masks are as shown here. So these are some images, these are some masks. And as you can see, when there is no crack, mask is just black. So black corresponds to background, white corresponds to object. Here our object is simply the crack. You might also wonder, do we actually need image segmentation here in this case? Why can't we maybe do some thresholding, something like Otsu's thresholding or something, where we generally suppress those pixels with high pixel values and retain those pixels with low pixel values, because whenever there is a crack, those cracks will appear dark in color. It is probably possible to do, but the thing is, in such an algorithm, there is no learning involved. We are just keeping a hard defined criteria to say what is a crack and what is not a crack. But here, because we are providing a mask, the mask will serve as a way in which the neural network can learn that in this case, for example, there are actually a lot of black colored dots, as you can see here. But the mask is showing nothing, which means none of these undulations on the surface is being considered as a crack by the definition of mask. So, and because of that, hopefully, when we feed an image that looks like this in the validation data set, it will again give us an output which looks like black color. It will not annotate every single black pixel as a crack, because that's not true. Black pixels, undulations are not cracks. So this is the sample data set. And then we define the UNet architecture. Definition is super simple. We have the convolution block in which one convolution, one ReLU, then again another convolution and another ReLU. One difference here is that in the previous lecture, we had also done a block normalization inside this. So convolution, ReLU, block normalization, batch normalization, which we are not doing this time. We can do it, we cannot do it. So in the original 2015 paper, they did not do it, but in the case where many people were implementing it, they were generally implementing batch normalization also. And then you have 4 levels in the encoder, and then 4 levels in the decoder. Decoder 4, 3, 2, 1. Okay. So I'm not going to explain the UNet architecture now because we have spent sufficient amount of time. Then we define the forward propagation, which is going from level 4 to level 1 to bottleneck. through encoder, and then in decoder level 4 all the way till level 1. Then in the training setup, I had originally played a little bit with the learning rate, and I saw that if I was keeping the learning rate as 10 to the power of -4, I was not getting convergence. My output was very, very bad. I had also tried with 10 to the power of -2. That was also bad. So for me, the sweet spot, I just manually found out. I did not run any hyperparameter tuning, but just manually found this to be the best learning rate for me. But feel free to try different learning rate, whatever works for you. And then number of epochs 20. So the reason why I want to run here 20 is because we will be uploading the same model to Hugging Face. So please make sure that you are running this for 20 epochs so that you have a good model. Okay. So once you have finished running the code, just let me know if you have reached this part. The final thing which is of interest is this line, saving the model weights. So can anyone confirm if you have finished running the model and if you have these weights, this line also executed? Once this is executed, you should see a file called UNet weights v2.path over here. Right now, I don't have it because I haven't finished running this. So just let me know. Can anyone let me know if you are managing to run this halfway through or something? Then I can proceed to the next step. Oh, you did not. Okay, here is the collab link. Just take a copy, and there were 2 Google Drive files. First one is the concrete crack dataset file folder. This is the folder for concrete crack. So please make a copy of that. For the next code, it's aerial segmentation, but that I will share later. I already shared it once, but I'll share it once more. So just let me know if you have been able to run this. Now, what we will do is once this finishes, right? We will just take some random 4 images as the input for evaluating the model, and then we will try to make a prediction. And for those data sets, since we already have the ground truth, we can compare again. So these are some outputs that I have. So here input is this, ground truth is this. Prediction is not so great. I mean, it's good, but not so great. I have just run for 20 epochs. I could run for a bit more to make sure that the model is not under-trained. But here you can see that in some cases, when the ground truth is purely like a black image, in the prediction, there are some white spots coming. So you can see that there is some white spot being predicted here. Here also, there is some white spot being predicted here. And at those locations, you can see that in the input image, there is some small black color undulation here, which is detected as a crack in the prediction, but not in the ground truth. So according to ground truth, it is not a crack. Here also, this small black color dot, according to the ground truth, it's not a crack, but according to prediction, it is a crack. So this is what we have. Now, what we are going to do is, please open Hugging Face. So just go to Hugging Face, just Google Hugging Face, and just go here. And then let me share an account where I don't have, okay, maybe I can show it here itself. Just go to Hugging Face and create an account using your email. It doesn't matter whether you provide it as a company email or personal email, does not matter. If you already have an account, just let me know that. Then what are we going to do here? We will upload, we'll upload 3 things, but all of them are not used here. We will upload the data set. We will upload the trained model. Then we will upload another code, which is for hosting the Hugging Face application. The application would look something like this. I have already posted it here. If I go to Vishwara and this UNet crack detection, this is a hosted application where you have a nice user interface. In this user interface, I can upload a random image with crack. So here I could upload this. So this is an internet image. I did not even get this from my data set. I randomly went to Google, asked for concrete crack. And here, if I submit this, automatically the evaluation will happen using a pre-trained UNet, which was trained by me. Then I uploaded the weights of the UNet, and then here it's detecting the crack. So this is what we are going to do. But what is Hugging Face, first of all? Hugging Face is a platform where many different types of models are hosted. There are also data sets hosted. So for example, if you search GPT OSS, the open source model of GPT, you have this 120 billion parameter model hosted. You can actually inference the model. So there are people who have hosted the model such that you can play with it. So here we can say, hey, what are your capabilities? So this is as if you are chatting with ChatGPT, but you have a open source model hosted using, I would say, Fireworks provider, right? And then you can chat with the model here. Similarly, in segmentation also, if you just go to models, then if you click tasks, click image segmentation, here bunch of models will appear, which are already existing models, which are pre-trained with huge number of downloads meant for segmentation. And here, if you sort it based on, let's say, most likes, then you will see some amazing models which can be used for segmentation. But if you want to try out a model for segmentation, you can go to Hugging Face Spaces, in which you will see hosted applications which are ready to run. And here, if you search image segmentation, so there is a model which was called as mass generator segment anything. Okay, let's try this segment anything web. And here I can upload some random image. Okay, not this. Okay, this is an image of myself. And here it's processing the image to detect different regions. And yeah, let's wait for some few seconds. And meanwhile, I want to show you one more Hugging Face model. So let's say in the last lecture, we discussed about this Dino V3. So in the Dino V3, so in this link, you can get inference on Dino V3. It was actually available till yesterday. Let me just check once more. Yeah, I think this one. Okay, you are getting an error saying list out of index range error when running the code. Can you tell me in which line are you facing the error? It might show like in which block are you facing the error? Is it somewhere in this one? Perhaps in the dataset creation part, because that may happen if you're duplicating the Google Drive folder is not fully done. I was getting some error similar to this. Yeah, get one batch. Okay, can you go to the Google Drive folder and see if the data set is actually there and it has two folders, images and masks. If those two folders are there and if those folders are not empty, I think it should be fine. Okay, meanwhile, our segmenting is done here. So here, if I move my mouse on different parts, see it has nicely segmented person, these glass panes, this background, then this wall. So I'm just moving my mouse pointer to select those segmented regions. Super cool, right? So this is like how we can make use of hosted models on Hugging Face for quick inferencing. This Dino V3 also is supposed to work. I'm not exactly sure. We can try an example. Maybe that is better. Anyways, meanwhile, this is loading. I'm not sure if this particular application is right now active or not. It seems active, but it's not working for me. Anyways, now what we are going to do is we will, once you have created the account on Hugging Face, we will see how to push the data set into Hugging Face, right? So we have this concrete data set. So we will create a repo on Hugging Face itself, and into that repo, we will push the data set. So first, you will have to install these two things. This data sets is from Hugging Face and Hugging Face Hub. So I'm going to copy paste these two lines. Just run this on Collab so that these two libraries are installed. Okay. And once that is done, you can mount your Google Drive folder with the concrete crack data set. I don't know if your folder name is this concrete crack or something else, but whatever it is, change the name appropriately. This name to whatever is your folder name. It should be concrete crack data set unless you do something with the folder. So just run that. Then the third thing is we have to log into Hugging Face using a certain API. So I will tell you where to get the API from. But before that, let me connect the Google Drive folder. And to get the API, go here, go to Hugging Face, click on your profile account, and there is a section called Access Tokens. So click that. And then here you can create a new token. So click Create New Token, name it as something, Hugging Face _ token. And then in the permissions, I usually provide all these repository and inference permissions. And here in the organization, if your Hugging Face organization has a name, just select that name. In the repo, since this is for creating the repo, I guess you don't need this, but otherwise you will have to select the repo in which you are going to make the change and just give the repository permission to this organization inference. Or if you simply want to just provide read or write permission, if you want to just provide write permission, just click write instead of fine grain. That might be easier. Then create a token. Then whatever your token is, copy that. Once it is done, I'll be deleting this, of course, but copy that and then go back to your Google Colab code, run the login. And here it will ask you for a token. So just paste it here. So I will share this code also with you. Just so do this on a different Google account so that the previous UNet training is not getting interrupted. So I'm just going to share the Google Drive link with you. Google Colab link with you. So just use that and here paste the Hugging Face token. And now you are connected with Hugging Face. And then you're going to create a repo. So in the repo, two things you have to notice. One is your Hugging Face username you should use here. And the data set, if you are uploading the data set, just whatever name you want to upload. So here I already have a folder called concrete crack dataset on Hugging Face because I had done this before. But here I will put it as version 2, V2. And I will set it as a public dataset instead of private dataset. So you can also see it. So when I run this code now, it will take some time because there are some images in this dataset and it will take some time for me to run the code. Okay, so here it's throwing an issue. Issue is that it does not have all the permissions that it requires. So let me just go back to my Hugging Face and maybe create a token. I'm using another token, which I had created earlier, and login. Or maybe I'll just restart my session so that everything is starting from clean. So what we are going to do now is we will create the data sets in Hugging Face. It has three things: data sets, spaces, and models. So model, we will upload the trained UNet model, the model weights. In the space, we will host the application where anyone can come and upload a cracked data set and infer from it. So this was my application which was hosted earlier. So I'll share the link with you. It should be a publicly accessible app. So just check out this app. And if you go to Google, download any, just in Google, go and search concrete crack. And if you upload that crack image here, and if you submit, ideally, you should be able to get the segmentation. Just let me know what's happening. So this is what we are going to do. And we'll run the Hugging Face login, paste the access token. Oh. Is anyone at this stage where they have finished the finished running the unit training part? Also, just let me know once you run the crack detection Hugging Face app, the one which I just pasted now, whether it's working for you or not. Just let me know. But at the end of the day, it should be a hosted app that's working perfectly fine for you. Meanwhile, I'm just trying to figure out what is the issue with respect to these permissions. So I'm creating a data set manually called V2 private publicly, and then I just want to try with this. So I just created the data set, and it will look like a GitHub repo, but empty. So this the way this is managed is using Git for version control. So right now it's empty, it has nothing. But what we can do is now go to the access tokens, and in the access tokens, just let's invalidate this, or let's just edit the permissions of this. And here I can change the repo to dataset v2. And here I'm giving all the permissions, read, write, everything. And now hopefully, if I create a new access token, copy it and paste it in my login, I should be able to access that. Anyone facing similar issue, fine grain to write? Let me just try. Okay, I think there is still an issue. I'm just checking if there is any spelling issue or something. So my repo name is, just let me know if any one of you are facing a similar issue. Basically, I have this dataset repo called Visuara/concrete crack dataset v2. And I just want to connect to it to upload the dataset, right? So this is the data repo ID, Visuara/concrete/crack-dataset-v2. And I'm logging in using the right permission, but for some reason it's not working. To all your orgs resources and can make, okay. So creating the token, it has right permissions, just copy it. And disconnect runtime. Wow, this is still not working. Let me just check if I need to do something which I'm not doing correctly. And meanwhile, let me know if for you also this code is showing the same error. Basically, the error that I'm getting is I don't have permission to write to this repo. Incorrect username. I don't think username is wrong. Okay, for a moment, I'm just giving all permissions. I don't think that's the best practice, but just want to get this to work. So here in the orgs, I have these. Okay, so now that I have all permissions, hopefully this should work. This is a weird error. I have not noticed this error before, other than just making a spelling mistake. If any of you know how to fix this error, that'll be great. Basically, the error that I'm getting is I don't have permission to my own repo, but I do have clearly. Okay, now it seems to be working. So what I did was I replaced this code, repo ID and create repo. So instead of asking to create a repo, because that repo already exists, I don't know why this error was happening. So I'm just going to comment this out so that not causing an issue later. What I did was I copied this particular code from Hugging Face itself. So in the dataset card, Hugging Face provides command line interface, Python code, or other forms of codes for you to push items into your existing repo. So here it gave this code and I just copy pasted that in. Okay, let's see what prediction. Yes, I was also getting the similar error, Anita. So what is your learning rate right now? That is clearly wrong. The prediction is clearly wrong. My learning rate is 10 to the power of minus 3. and my loss is reaching 0.00114. So, and because of that, my prediction is good. But if this is something like 0.2 or 0.4 or something, then I was getting a prediction like completely black mask. So just let me know what is your loss. Just try playing with this learning rate a little bit. It might, okay, loss is 0.45, yeah. And how many epochs? You also ran 20 epochs, right? Yeah, yeah, I think you should definitely run for more epochs. I was getting the same error like when, can you do one thing? Can you try increasing the learning rate? If it is 10 to the power of -3, try 5 times 10 to the power of -3 or something as the learning rate and see if the convergence is better. Then we can see. Anyways, my Hugging Face is now working, thankfully. And currently it's uploading the data set. So one thing that I found to be weird is the dataset folder size is actually very small. It's just 7 megabytes. But still, it takes a little bit of time for us to upload the dataset. And once we upload the dataset, it will look something like this. So go here, go to the go to this dataset. So this is the one which I uploaded previously. And it has, so once you have uploaded it, it will nicely create it to something like this. First of all, it's not classes. Okay, so this part is anyway wrong, but the data set will look like, if you go to files and versions, there are two folders. One is images, other one is masks. In the images folder, there are a bunch of images. In the mask folder, there are corresponding images which are masks. Okay, so this is ultimately what we wanted. But this data set, we are not going to directly use for inferencing. I just wanted to upload it here just to show you a good practice of creating the pipeline in Hugging Face. Next, what we will do is, while I'm running to upload in this dataset V2, this is anyway like for showing you as an example, we don't need it. What we will do is, if any one of you have managed to train the model and get the model to a decent loss, like something like 0.01 something, then just run this block of code, which is to save the model. Okay, so when you run this code, you will get this UNet weights underscore v2 dot path over here. So just click the 3 dots and download it into your desktop. So just let me know where you are till now, and then I'll tell you what to do next. So while your training is going on, let's do one more thing. Go to Hugging Face and let's create a spaces. So click your profile icon and click new space. And this new space is something that we are going to be hosting publicly. So we can name it as, I would say, UNet for crack detection in concrete. Okay, and then upload a cracked concrete image for segmentation. And license, I can pick MIT license, and I'll be using Gradio. So Gradio is the, we can convert Google Colab or Python code into a nice interface using Gradio. So we'll be using Gradio, and I'll start with the blank template. And this inference engine, which we are publicly hosting, if we want people to be able to use it in a fast way, we can pay for it ourselves and use these. But here I'll just use CPU basic, and then keep it public and then create space. So when you create the space, it will be initially empty, nothing is there. We'll have to create the files ourselves, and there are 3 files that we have to create. Okay, so first is, so go to the UNet for crack detection in concrete, click files. So go here and it should be currently empty. Here, click contribute, create new file, and we will name this file as app.python, app.py. And I will share the app.py code with you from my previous Hugging Face space, the one which I had hosted earlier. So this app.py code, just paste it in your app.py. So here, please notice what we are doing is we are defining the user interface elements. So first we are saying the saved weights. The weights is in a certain path. The path is Visuara/UNet crack segmentation. But this path you will have to change with your path, and I will tell you where exactly to change it. For now, just paste this code in the app.py. Okay, just sharing the code with you. So we'll need 3 folders here. One is the model itself. Actually, I'm not able to save this in the chat, so I'll just download it and I'll share the download link. Just try this. Okay, so for Anita, learning rate 10 to the power of -5 worked, is it? Okay, very nice. So increasing the learning rate did not work for you, decreasing it. Okay, very, very nice. Okay, I think this is very good. Excellent. So Anita, what you should do is just save your model by running this block of code, and then download the saved model from here. So here, if you refresh, it will appear, and just download it. Okay. And meanwhile, this link which I have shared is the app.py code. Just download that code also, and then you can paste it in your app.py. Next is the next file you will need is, so in my app.py, I'm going to paste this code. And commit. So when we commit, each time when a change is made to this repository, automatically the app will start building, just like in web app for continuous deployment and continuous integration. This is how it works. Then the next file that we need is the model itself. So the model folder can be named as something like unet_model.py. So to create a file, unet_model.py. So what we are essentially doing is we have to define the front end so that when we host the app, there are provisions like buttons to click and upload, etc. We need a place to store the actual model, not the weights, but the model architecture itself as a function. So that is what we are doing here. And that function is looking like the unit definition. So this unit class was defined in our code, in our training code. Same thing we are copy pasting here. So just let's paste it here, unet_model.py, and just commit that. The third is you will need the weights, basically the model parameters. Which model parameters? The one which you trained. So the one which Anita you have trained right now, you can download it and upload it in this space. So in the spaces, if you go to the files, currently you should have only 2 files. One is app.py and one is unetmodel.py. These 2 are default files, so ignore readme and git attributes. But these 2, app.py and unetmodel.py, should already be there. And then on top of it, you'd say upload files. And in the upload files, just upload from your computer, the one which you had downloaded from Google Colab. For me, it is this unet_weights_v2.path.pth. Then just upload it also. So now once this model is uploaded, this app will again start rebuilding, and it should be hopefully ready for deployment. So just to reiterate what we have been doing in Hugging Face is, first is we go to Hugging Face and create an account. So in this, there are 3 things which we will be doing, or we are doing. One is uploading the data set. Second is uploading the model. And third is creating a space. In the data set, we are simply uploading the concrete crack data set. We are not using it, but it is just for a good practice of creating a Hugging Face data set. In the model, we are uploading the UNet pre-trained. And what is this pre-trained on? It's pre-trained on concrete crack images. In the spaces, we are uploading 3 files. One is app.py. This is where the Gradio code is defined. Gradio for creating the user interface for uploading the image, etc., like an app. Second is the UNet model itself. So UNet model unit underscore model dot py. And the third is the weights, the unit pre-trained weights dot pth. So these three things we upload in the space, and in the model we have unit underscore pre-trained. But while we are hosting the space, these two things are not being directly used. I just showed you how to create the data set in Hugging Face and how to upload a model in Hugging Face just as a practice. But for creating spaces, we are anyway only looking at these three files. Okay. The Python model for UNet was already predefined here in our code. This guy. This UNet code is what is being used, this class UNet. So that code we copy pasted along with the torch library, import torch.nn as nn. So those two things we uploaded. I think there was a requirements.txt. I'm not sure if I had to upload this here or not. But anyways, then the second thing was in the app.py, in your case, you will have to define two things differently. One is the path to the model. For me, it will be whatever is the path to this guy. And second is you will have to custom define path to your pre-trained weights. Pre-trained weights. For me, the pre-trained weights are this. So whatever is the path to this file is what I need to provide. So for you, the only place where you will make changes in this app.py, go to this repo ID, and whatever is your repo ID, you should use that. And the file name, whatever is your file name here, you should use that. The other thing is the unit underscore model, right? The file name that I have used for my .py file is called unit underscore model .py. So if you are using that name, then you can say from unit underscore model import unit. So import unit means that class name is unit, but the file name is unit underscore model. But if your file name is different, you will have to make that modification here. Okay. So now let's see if our app is ready to just check, ready to infer. So I have two apps. This was the earlier one. I think this is the current one. It has a runtime error. Okay, no module name torch. So I have to add a requirements.txt in my repo. So I can add torch, and I can add, because when this is added automatically, those libraries will be installed. And I will also need maybe Gradio, I guess. So this requirement.txt is one way to tell your Python code that, okay, these are the packages that you will have to pre-install. So just do that as well. So just let me know if anyone managed to create this Gradio app yet, or if you are facing any error while creating this. So here you see this is showing building, and the reason why this is being shown is because I just changed that. I just introduced that new file requirements.txt, which is why it's currently building. So whenever a change is made, just like when you make a change in the GitHub repo, if it's connected to Vercel or something, that change will trigger a deployment, right? Same thing is happening here. But if everything is fine, if all the packages are properly installed, hopefully you should see things working. But let me check the log to see what package is missing. And meanwhile, let's also run the other code for running the aerial image. So I'm going to share the aerial image. I had shared it earlier. So somebody has shared the aerial segmentation Google Drive link right now. So please check that. That is the Google Drive link. And aerial image, for that, I'll have to install this segmentation underscore models underscore torch. So please uncomment this line and run this once if you have not run it yet. So this will install this particular segmentation model, PyTorch segmentation model. And then just run the code. And at the inferencing, what I'll show you something. If you are running only for 2 epochs, this will be a very, very bad output. I'll just show you how my output looks like because I just ran for 2 epochs compared to ground truth. And meanwhile, the Hugging Face space is being built. I think one more error might happen because I'm not sure if I have added all the required packages in the requirements.txt. So I'll have to check that. And so in both of these codes, please note, we are not running UNet++ or Residual UNet or Attention UNet. We are still running UNet, the vanilla UNet model. So please don't get confused. Yeah, so here, this is another part where you will have to make some change. I've run for only 2 epochs, but I would say it's better to run for like 20 epochs or something, but I did not want to wait. So I just want to show you what the output looks like with just 2 epochs. It's not very good. I also tried one more thing, which was using this exact same model for segmenting from videos. So the videos that I was looking was this pixels aerial view, something like this. So I tried for a video that looked like this, an aerial view video, but the segmentation was very, very bad. It's probably because in this case, the segmentation data set, right? It's extremely small. If you look at the folder structure, I have only around 50 or 60 images. This is not at all a big data set. I deliberately chose a small data set simply because I did not want to spend too much time during the lecture for training. But here, if you look at it, there are like 1, 2, 3, 4, 5, 6, 7, 8, 9, some 9 images and 8 folders. So totally like something like 50 or 60 images max. So in any case, we should not expect very good accuracy. But what I recommend you do is there are some aerial segmented images, big data sets with thousands or tens of thousands of data points, perhaps on Kaggle or other places. So if you train your UNet model with that data set with sufficient number of images, so here I'm not sure how many. I think this is also the same data set, this Dubai data set. Exactly, this is the one that I'm using. But we need something better for using for a general purpose aerial segmentation. So whichever data set you find, maybe from Hugging Face or elsewhere, just try training your UNet and let me know what kind of result you get. That could be your next assignment. So let me just note down what is that you're supposed to do. First is find more extensive data set for aerial images. Then construct vanilla UNet. Then train this model. Yeah. So collab link, I just shared, right? I thought I already shared, but I'll share it with you anyways. This is the collab link. So just do this, train the model. then save the weights, then convert to a public, public Hugging Face space. So there you will be using three things. app.py for just defining the radio interface, the pre-trained weights, and this will be the model itself, whatever unit model you are using, .py. This will be like .pth, and this will be .py as well. So these three are the files that you will need. And of course, you will need a requirements.txt file for mentioning your packages which are required. And then share the link. I'll post an assignment, but you share the link in the assignment. And what I will be doing to test your model is I'll be picking random aerial images like satellite image or big drone images from the internet. And I will be putting it in this inference engine hosted on Hugging Face to see how good the segmentation is, right? It will be a very nice exercise for you to build this whole pipeline. But here, yeah, so this is my output, right? You see the quality is kind of not very good. All these things, whichever is black pixel, is being segmented nicely. Some of them are these blue roads. Some of them are being identified nicely, but prediction is not at all good. Mainly because my epochs are just 2, and you can see that I'm still under training significantly. You could bring this down by a lot. So I'll just keep running this for 20 epochs on the side, and I will try to make this better. But please note, if you just paste a Hugging Face, I mean, this code from your current aerial image dataset base code, it will not work because the dataset size is very, very small. It's just what I said 50, 60 images. Ideally, in my opinion, there should be maybe 5,000 images, because the number of classes we are segmenting are maybe 8 classes, right? So 1,000 images per class, or 1,000. There should be 8,000 images, hoping that predominantly each image belongs to one class, although in every image there are multiple classes. So something like 5,000 to 10,000 images might be good to have in the data set. But obviously that will mean that your training will take time. You may have to run the training overnight. So just do that. And to make sure that your screen is not dying, as I showed in the last lecture, I have installed this plugin, this extension called Wake Up or something. What is this called? Keep Awake. So this just install this Chrome extension so that it's on this screen awake mode. But once this is finished, I just want to show you the result. I might be posting it on Discord. But I think this is a good time to wind up the lecture. But I just want to take a brief recap of what we learned in UNet. So UNet is a fantastic architecture for semantic segmentation. In the last lecture, we discussed the difference between instance segmentation and semantic segmentation. Semantic segmentation is you look at every pixel and you ask a question, hey, is this pixel belonging to class A or class B or something else? So you are only looking at the class. You're not caring about whether this is the 50th instance of the class or second instance or first instance. You don't care about number of times that class is appearing. So that is called semantic segmentation. We also discussed that it's useful in the case of, let's say, tissue classification into cancerous or non-cancerous. You don't want to draw boundaries between two cancerous tissues. You don't care about that. As long as the tissue is cancerous, you want that pixel segmentation, right? So that was the main idea behind semantic segmentation. And UNet is extremely good for that because of its unique encoder-decoder architecture. So it's called U because of its shape. This is UNet. And this whole thing is encoder. And this whole thing is decoder. And this bottom part is the bottleneck, and these are skip connections. So encoder will bring down the spatial resolution of the image, but increase the number of channels. Here it was 572 by 572 by 1 channel, but this was the spatial dimension. By the time you reach the bottleneck, it will become 30 by 30 by 1024. So spatially much smaller, but channel number wise much deeper. And then, so this will allow you to create many different abstract feature representations in the image in different channels. Then there were these up convolutions. We discussed in detail how exactly does the up convolution work. It works through bilinear interpolation. And then you can replace, you can restore some of the lost dimension by this up convolution. But this skip connection will also ensure that you are concatenating values which are more richer in features closer to your original input data from the encoder into the decoder. So this was the most powerful thing about this encoder-decoder architecture, very different from ResNet, because in ResNet, you are adding, here you are concatenating. Then in this lecture, we discussed about some other architectures like UNet++, where there are additional convolution layers in between in the skip layer. And this allows the neural network to learn much more deeper patterns rather than just directly passing the encoded features over here. You're also making it perform multiple convolution operations. You're also, if you look at the up convolution, there are layers from this being passed here, this being passed here, this being passed here. So it's like a much complex convolutional neural network architecture, but this also allowed to have all those slower training and slower inference, allowed to have much more better gradient propagation or back propagation. Then we also discussed briefly about the residual unit. Residual unit is nothing but inside this block of each layer of encoder and decoder, you have these residual connections which are adding. So plus means you are adding whatever is input is coming from here to here. So spatial resolution does not change. See, this is 64 here, this is 64 here. This 64 is not becoming 62 because you are probably adding padding. And here you see 128 is remaining as 128. Otherwise, you can't add. How will you add two different filters? Two different features of different spatial dimension. You can't. Otherwise, you'll have to crop and add, which was being done in the skip connection. Then after that, we finally also discussed about attention unit, just from a theoretical level, not from an implementation level. Just the concept that people were doing were here, they were filtering out the features coming from the skip connection for relevance. And how did they find this relevance? They constructed as something like an attention map, like using alpha. So the map was something like this, where there are numbers of alpha ranging from 0 to 1. So if alpha value in let's say this cell is close to 0.9, the feature corresponding to that cell will have high relevance. If it is close to 0, it will have very low relevance. So this was the idea behind kind of refining the skip connections using this attention gate. And this resulted in slightly better segmentation. But at the end of the day, if you look at popularity, if you look at the massive adoption, the vanilla UNet is still massively adopted. And one last thing is, as I showed you in the last lecture, UNet is also used tremendously in diffusion models. So if you search UNet diffusion model, you will simply see this architecture where you can see that this denoising part here is basically a UNet. So UNet was literally, I would say, revived, and maybe 1/2 of the citations that came for the UNet paper, it has 118,000 citations. Half of them might have come because of its relevance in stable diffusion. And then today we implemented the UNet model for these two data sets. One is the concrete crack data set. Another is aerial image data set. Both were technically like a toy data set, mainly because of the size. Data set size is not very high. One of them has around 700 and something images. The other one has only 60 images. But because of the sheer size of the data, in terms of megabytes, see here 20 epochs are just finishing, right? It's taking time for us to perform the training part. Inferencing is fast. So see here, now this is the new inference after my 20 epochs, slightly better, but not as good as it could be. But this is what we have from the UNet segmentation. And we don't deserve any better because the data set is very small, which is why I want you to try out on much bigger data set. The last thing is we discussed how to create Hugging Face spaces, data set, and models. In the spaces, in the Hugging Face, we'll be uploading a grad.io app.py. We will be uploading the UNet architecture itself. So app.py has the definition of the front end for our application. This unit model.py has literally the class that defines the unit. So the way we will be importing this into our app is just like how we import any other library. Just check this. From unit underscore model, import unit, right? This is exactly how we import any library into our Python code. And then the last one is our pre-trained weights. So these are the pre-trained weights of our unit, which we trained using the concrete crack data set. And at the end of this, when we post it, we should be able to see that here. Okay, so here there is another runtime error, which is because I think, yeah, so torch vision is also missing. So I have to modify my requirements.txt by adding torch vision. So whichever modules this code is supposed to have access to, we should add all of that in the requirements.txt. So torch is needed, torch vision is needed, maybe Gradio is needed, maybe NumPy is needed. So I have to check which all Python libraries I need to add in the requirements.txt, and then it will work. I was facing the same error before hosting this. And once you host it, it should be a publicly accessible link like this. So this link, when I paste it in the chat, hopefully this should be accessible to you publicly. I think I hosted this publicly only, not privately. And this is what the application will look like. So you can go to internet. So go to internet and search any concrete track image and find any random image. Just download it. So save image as, and then go to our app, click to upload this downloaded image. Yeah, this one, I think. And if you submit this, our unit pre-trained model, which is hosted on Hugging Face, will perform the inference. And after inference, you see it is showing us the segmented region. So it's amazing. I mean, it's a very good model. The only thing is all the images are looking like either black or white. But this will also work, I think, for pipes in which there are cracks. So one of the companies that I'm very familiar with, their business model was partnering with big industries like oil and gas industries and passing like small drones through their pipes. And these drones will image the insides of the pipes, and then it will detect cracks or any defects that are there in those pipelines and will give us feedback. So there are many ways in which this feedback can be collected, but visual feedback is one of them. So there are very interesting industrial use cases for detecting defects or cracks in these massive installations. So with that, we can wind up today's lecture. So please work on the assignment. I think it will be a very good exercise for you to build it yourself rather than just watching me build it. And please, once you submit the assignment, just post your Gradio link on the Discord also, so others can try out your app. It'll be cool, right? And if you can build any other app for other than aerial images, maybe let's say for natural images like outdoor images, segmentation, because you can train this on any data set, on Cocoa data set or any data set. So it'll be great if you can train this on data set, host it as a Gradio, Hugging Face space link, and others can work on it, right? So thank you so much. We will meet again. Oh, so there is one update which I want to share with you. So next week, I'm traveling for 2 weddings. So there is a small chance that we won't be able to host the lecture next week. So the next module is supposed to be YOLO. So we'll have to push it by 1 week. So there are 2 more modules remaining, 4 more lectures, 2 lectures on YOLO, 2 lectures on RoboFlow, on how to create pipelines. So in RoboFlow, I'm planning something interesting where all of us can together work on annotating a data set, creating an actual industry use case solution. So, but there we will most likely use YOLO. So I have to first cover YOLO before covering RoboFlow. So I'll communicate this through email to all of you, plus also on Discord. So please just notice that there is a small chance that next week we won't have lectures. So thank you so much. We will meet again whenever next lecture will happen. I will keep you all posted. So thank you so much. If you have any doubts, just post it in the Discord. See you. Bye.